Chapter 7 begins our work with the inverse functions. And to get started, we need to go back and think about the graphs of the basic trig functions. So let's start with the sine function. If you recall, when we unwrapped the sine function from the unit circle, we had a graph that looks like this top function here. It has a domain of all real numbers and a range restricted between -1 and 1. And if you think back to the end of the Math 150, to the end of Pre-Cal 1, we had a section about inverse functions. And one of the main things that we had to look at was before we could find the inverse of a function, we had to have a one-to-one function. What that means is when we do an inverse of a function, we want to make sure that what we end up with is still a function. So, of course, because of the periodic nature of the original sine function, it is not one-to-one. So we have to restrict it. And that's what the second graph is coming from. They just picked a chunk out of it. They chose to go from -pi/2 to pi/2. Different books do different things, but this is sort of the convention. So for this restricted function, we have a domain from -pi/2 to pi/2 inclusive. Notice that you've got the less than or equal to on the domain here. And the range is still restricted between -1 and 1. And if you think back again to that section on inverses, what happens now is we're going to invert our little function over the line y equals x. This is going to switch the x's and the y values. So the domain becomes the range becomes the domain. So the inverse sine function. Okay. Notice that this is now my domain between -1 and 1. This is now my range between -pi/2 and pi/2. Notice that both of those are less than or equal to. Okay. The new notation is this. And the thing that you need to keep in mind is whenever you see that sine to the -1, okay, so let's write the inverse sine of x. Whenever you see that, you say to yourself, okay, this is going to return an angle. This function value is going to be an angle, and it must be restricted between -pi/2 and pi/2. Okay, so you just kind of keep saying that to yourself. All right, let's do the same thing with the cosine. Here's the graph of the cosine function. Also, a periodic function, domain of all real numbers, restricted between -1 and 1 for the range. And this time, we want to, again, pick up a little chunk of it so that the piece that we have is one-to-one so that we can invert it. And this time, notice they chose to go between 0 and pi. And it's a kind of an interesting decision, but if you think about it for a second, if we went from -pi/2 to pi/2 like we did with the sine function, we would only have that little top piece of the function, so we would be missing all of the part that's below the x-axis. So it does make sense that they shifted it over for this one. You do have to kind of keep that in mind. Again, this is our restricted function here at the bottom. Domain going from 0 to pi inclusive, so less than or equal to on those. And again, the range going from -1 to 1. To do the inverse, we're going to switch the x's and the y's as we flip it over the line y equals x. The domain becomes the range becomes the domain. We come over, and this is what we have. Notice the domain is now from -1 to 1. The range is now from 0 to pi. And again, this notation, the cosine to the -1 of x, read the inverse cosine of x, keep saying to yourself, it returns an angle. It can't return any angle because it has to be restricted. Where was it restricted to? Between 0 and pi. So whenever you see that symbol, you know you're going to give an answer that's an angle between 0 and pi. Okay. We can do the same thing with the tangent. Again, we must restrict it. This one also, the domain was all real numbers, okay, except for what? Except for the odd multiples of pi/2. That's where you had your vertical asymptotes. And the range was anything because it runs increasingly up or down. So we're going to restrict it again. They went back to the -pi/2 to pi/2. Again, that's the convention. Some books do 0 to pi, but our book does -pi/2 to pi/2. Notice that this time when we do the restriction down here, notice that we can't have the or equal to on the x's because that's where the vertical asymptotes are. Okay, so that's a little bit different. And then here your range is all real numbers. So we're going to invert this one as well. Switching the domain and the range, going to get something that looks like this. Now again, the range became the domain became the range. Okay, so the inverse tangent is going to return an angle. It's going to return an angle between negative pi over 2 and pi over 2. Okay, and again, it's important to notice that it does not have the less than or equal to on it. So they give us these properties of the inverse functions, and I just picked them up out of your book. And it can be really confusing when you look at these, but what you need to remember is they don't just necessarily cancel out, okay? So look at this first one here. So the inverse sine of the sine of x is x, only in certain cases. Which cases? The cases where the x's are between negative pi over 2 and pi over 2 inclusive. Okay? So again, you see this symbol. You say to yourself, I must get an answer that's an angle. It's in that restricted domain between negative pi over 2 and pi over 2. If this little guy right here, that argument happens to be between negative pi over 2 and pi over 2, then you're lucky. They do essentially give you back the x. The inverse sine of the sine of x gives you back x. Plenty of times, though, we'll work these problems, and the argument inside here won't be in that domain. Okay, so it won't be where it's between negative pi over 2 and pi over 2. So we have to do a little bit more work. Okay, same thing down here with the cosine. Remember, the inverse cosine must return a value between 0 and pi. So I must look here. The only way you're going to have the inverse cosine of the cosine of x literally equal x is if that inside argument is a number between 0 and pi. Okay. And for the inverse tangent, same deal. Inverse tangent must return a value between negative pi over 2 and pi over 2. The only way the inverse tangent of the tangent of x is if that argument is restricted into the negative pi over 2 to pi over 2. Okay. Going the other way, remember, you can think of the functions we just looked at for sine and cosine and tangent, or you can think back to the unit circle. Sine must give you an answer between, a sine function must return an answer between negative 1 and 1. So again, you look right here. If this value happens to fall between negative 1 and 1, then we can say that the sine of the inverse sine of x is x. Same thing for the cosine. This argument must be between negative 1 and 1 if we're going to say that the cosine of the inverse cosine of x is x. And this one, we like this one. This one works out well because the tangent of the inverse tangent of x is x as long as x is a real number. So that one's cool. So yes, these are properties that are very important, but you also have to make sure you understand the notation. Just keep saying to yourself what the symbols mean and reminding yourself which one returns just a number and which one's returning an angle measure. We have all of the same things for the secant, the cosecant, and the cotangent. It should be pretty familiar if you think about the fact that we're doing what the inverses of the original cosine, sine, and tangent. So the inverse secant, the inverse cosecant, and the inverse cotangent, these are all their definitions. The one thing to keep in mind, though, is notice that when you get to the cotangent, notice that it goes from 0 to pi. And what happened with the tangent? Go back and look. With the tangent, where is it? The tangent went from what? Negative pi over 2 to pi over 2. Okay, so that is a little bit different. So you got to keep your eye on that one. All right, and it has a little note here to go and look back in your book if you want to see the basis for the definitions. Okay, so then I have just gobs of practice problems. We're going to work on some of these in class, but I also wanted to show you, just give you some written examples. All right, so we're going to find the exact values of the expressions. We're not going to use a calculator, and we're going to see what we get. Let's start with the inverse tangent of root 3 over 3. Okay, so I'm going to get an angle, and I don't want to use a calculator, so I can think of my base graphs that we just talked about, or we can go back to the good old unit circle. Honestly, that's where I tend to go. All right, so I'm thinking unit circle. I'm thinking, what angle is going to give me a tangent value of root 3 over 3? So, where am I thinking? So, let's see. Root 3 over 3 is rationalized, so that came from 1 over the root of 3. So can you picture what that would have had to be? It's where the sine would be, what, 1/2, and the cosine would be root 3 over 2? Where is that? Can you picture it? So I want the sine to be 1/2, and I want the cosine to be root 3 over 2. Isn't that at pi over 6? Okay. So this question is basically saying, give me the angle that has a tangent value of root 3 over 3. I know that's 1 over root 3 before I did the rationalizing. So I'm thinking in my head, I'm thinking unit circle. I'm thinking I need the 1/2 over the root 3 over 2. So the sine over the cosine, it's pi over 6. Okay? All right. Now let's look at number 4. The inverse sine of the negative 3 pi over 7. So this is one of those we were just talking about where we said, well, the inverse sine has to return what? An angle that's in between negative pi over 2 and pi over 2. So the only way that I can say the inverse sine of the sine of negative 3 pi over 7 equals negative 3 pi over 7 is if I am confident, and I know, that negative 3 pi over 7 is between negative pi over 2 and pi over 2. Okay? Now, just think real quick. We know that negative 1/2 is 0.5. Negative 0.5, we know positive 1/2 is 0.5. So can you figure out what is 3/7 as a decimal? So let's see. It's going to be 0.4 or something, right? Okay, and it's going to be negative because this is negative 3/7. Yeah, this actually is between negative 0.5 and 0.5. So this is one of those where it comes out lucky. The argument of the inside function is between negative pi over 2 and pi over 2. So I can say that the inverse sine of that argument is negative 3 pi over 7. Check it again with the second one. The cosine of the inverse cosine of negative 2 over 3. All right, again, thinking. Cosine returns a value of what? So the cosine of whatever gives me an answer between negative 1 and 1 if you think of the unit circle. So if I want to say that the cosine of the inverse cosine of negative 2/3 is negative 2/3, I have to have the negative 2/3 between negative 1 and 1. Is it? Yes, it is. Okay, so another one where we got lucky. Okay. All right, what else have we got? Oh, here's some more. Again, same directions. Find the exact value of the expression. Don't use calculator. Now, this time we are way away from the territory where they're going to cancel each other out because we're doing the tangent of the inverse sine of negative 1/2. Okay, so again, think in unit circle, right? This first piece right here, the inverse sine of negative 1/2 means give me an angle that has a sine value of negative 1/2. Okay. So, let's see. There's lots of them, right? But we're restricted. Where are we restricted? We're restricted into the first quadrant and the fourth quadrant because we want to go from negative pi over 2 to pi over 2. If we think about our unit circle, pi over 6 and negative pi over 6, and I drew those backwards, okay? So if this is pi over 6, this is negative pi over 6. I drew them as I was saying them, okay? So where is the sign? What angle has an inverse? What angle has a sine value of negative pi over 2? It's negative pi over 6, okay? So now we have the tangent of negative pi over 6. That is that. Okay, so now we're just back to what's the tangent of negative pi over 6? What's the tangent of negative pi over 6? It ends up being negative, fourth quadrant, 1/2 over root 3 over 2, which is 1 over root of 3. And if we rationalize, that's negative root 3 over 3. Now, I realize that when I'm drawing my unit circle over on the side, I'm not putting in all the details because it's just not going to fit on my screen. Please make sure you've got your unit circle sitting there beside you so that you can point to it and make sure you understand where these values are coming from. Okay, let's change colors. Let's go to green. Okay, I want to do the cosecant of the inverse cosine of negative root 3 over 2. Okay, so again, I'm in here. I want to find an angle that has a cosine value of negative root 3 over 2. And again, I'm thinking the inverse cosine, I don't get to use the whole unit circle anywhere I want. The inverse cosine was defined to be between 0 and pi. So that was this first and second quadrant. And since I've got a negative root 3 over 2, I must be in the second quadrant. So where's the cosine value? Negative root 3 over 2. Isn't that at 5 pi over 6? Okay, so the inverse cosine of negative root 3 over 2 is 5 pi over 6. Again, because we're restricted for that inverse notation, that inverse function is restricted between 0 and pi, that's the only angle that I can give as that answer. Okay, so now what's the cosecant of 5 pi over 6? Again, thinking again, cosecant. It's the reciprocal of the sine. So the reciprocal of 1/2 is 2. Okay, the cosine of the inverse sine of 2/3. Okay, let's do it one more time. Oh, I said 2/3, root 2 over 3, sorry. Okay, so the cosine of the inverse sine of root 2 over 3. Now this is the first one where we've hit, and that's not on the unit circle, right? That's not one of the values we know. All right, so let's think. The inverse sine of root 2 over 3 is restricted between negative pi over 2 and pi over 2. And if I'm going to get a positive answer, I'm talking about some angle theta that's got to be in the first quadrant. Does that make sense? Okay. The inverse sine of root 2 over 3 is an angle between negative pi over 2 and pi over 2. And since I've got a positive result, I want to be in the first quadrant. Let's see, how can we do this? I would go back to my good old Pythagorean identities. This inverse sine of root 2 over 3, I can say that the sine of theta is root 2 over 3. Could say it backwards. And then I could use my Pythagorean identities and solve for what I'm going to get for my cosine value. So the sine squared of theta plus the cosine squared of theta is going to give me 1. All right, so now again, what I'm doing, I should have written, hold on a minute, let me move this away from here. Go back here. This is some value theta, okay? So what I'm trying to find now is the cosine of theta. So in order to use my Pythagorean identity, I'm going to rewrite the inverse sine of root 2 over 3 is theta as the sine of theta is root 2 over 3 so that I can use my Pythagorean identity. Okay, I just wanted to make sure that I said that correctly. All right, so let's see. Let's put the root 2 over 3 in for sine of theta. And I'm going to solve for cosine. So this is what? 2 over 9 plus cosine squared of theta is 1. So cosine squared of theta is 9 ninths minus 2 ninths is 7 ninths. Take square root of both sides. Square root of 7 over 3. And positive, we're in the first quadrant. Okay. Let's see what's next. Oh, here's a few more. Find the exact value of the expression. Again, don't use the calculator. Think in unit circle. Okay, so the sine of 7 pi over 6. Think about that on your unit circle. Where is it? Right here. Okay, so the sine of 7 pi over 6, that's negative 1/2, right? So this is the inverse cosine of negative 1/2. Okay, now I need to find an angle that has a cosine value of negative 1/2. Inverse cosine is restricted between where? 0 and pi. Okay. So first quadrant, second quadrant. It's negative, so I'm looking in the second quadrant. Where am I going to end up? What's the cosine? What angle in the second quadrant has a cosine value of negative 1/2? Is it 2 pi over 3? And how about number 16? What's the inverse secant of negative 2? All right, think about what that means. So give me an angle that has a secant value of negative 2. So the secant of some angle is negative 2. So that's the same thing about thinking with the cosine, right? So that's the same thing as saying where's the cosine of theta equal to negative 1/2? Okay, so where's cosine theta negative 1/2? Again, you're thinking first quadrant, second quadrant, because you got to go between 0 and pi. So, isn't that 2 pi over 3 again? Convenient right after the top problem. All right. Now, these with the calculator, I'm just going to kind of help you get them set up. The first one, the inverse tangent of negative 3, you're going to enter it just exactly like it looks. There is an inverse tangent function on your calculator, so you literally are just going to hit second and go to that function. You should get negative 1.249 for this one. The ones that are interesting to get into the calculator are the ones that are the reciprocal functions. For instance, the inverse cosecant of 5. It's a little bit, you got to think through that before you can put that in your calculator. I tend to want to really go through and think to myself, okay, this is saying that the cosecant of some angle is 5. Well, if the cosecant of some angle is 5, then that means that the sine of some angle is what, 1/5? Because of the reciprocal identities? Well, then that means I can do, there is some angle with a sine value of 1/5. What is it? Then I can use my inverse sine function on the calculator. And you should get 0.2014. 4. Okay. Do it again. Do it with the secant. The inverse secant of negative 4/3, that's not a button that you're going to see on your calculator. Secant is a reciprocal of the cosine, so I can switch this. I can think to myself, so the secant of some value, some angle, is negative 4/3. Well, that means to me that the cosine of some angle had better be what? Negative 3/4. Then I can go back and say, all right, what's the angle that has a cosine value of negative 3/4? I can type that directly in the calculator, and I should get 2.419. We don't do a lot of the ones with the calculators, but it's a good idea to make sure that you understand how to enter them. So again, inverse sine, inverse cosine, inverse tangent, they're buttons on the calculator. Okay, they're functions that you can just hit. The reciprocal identities, the reciprocal functions, easiest to switch them back to sine, cosine, and tangent and go from there. Okay. So what about if I literally ask you to find me an inverse function? Okay. I give you this function. I'm going to go ahead and restrict the domain on it, okay? And I'm going to tell you to find the inverse. So if this doesn't seem familiar, you're going to go back to the beginning of chapter 5 in your ebook and look at how we did it with just the baby functions. Okay, but now we're going to do it with this. And one thing that I do like to do when I work on these problems is this domain and range question. I like to tend to it right at the very beginning. All right, so this particular sine graph, we're looking at the little chunk between negative pi over 4 and pi over 4. But think for a minute, what's the graph of it look like? If I were going to ask you to sketch it, what's the amplitude? Do you remember what that 3 does? Makes it go down to negative 3 and up to positive 3. So I know my range is negative 3 to 3. Okay. Now, the reason I like to do that from the beginning is because then I can come down here at the bottom and the domain for my inverse function is going to be negative 3 to 3, and the range for my inverse function is going to be negative pi over 4 to pi over 4. Just go ahead and get that done, okay? Because that's exactly what happens whenever we think about an inverse function and we flip it over the line y equals x. We switch all the x's and y's. Okay, I've taken care of that part. Now to actually find the function, do you remember how to do that? The first step was to switch the x's and the y's. So right this minute we have y equals 3 sine of 2x. Okay. So when we get ready to find the inverse, we literally go in and switch the x's and the y's. We'll change colors again. All right, so this y becomes an x, and that x becomes a y, and we're just going to solve for the little baby y. Okay. So let's see, let's divide by 3. So x over 3 is the sine of 2y. Oh, and we need to get at the y. So remember when we were doing exponential and logarithmic functions and when we had it in one form and it didn't work, we switched it to the other? Okay, we can't get at that y in this form. We need to switch it to the inverse sign. So this is the same thing as what? This is the same thing as saying the inverse sine of x over 3 is 2y. Just switching the form. The sine of 2y is x over 3. So the sine of this value is x over 3. Okay. The sine of the angle gives you the value. The inverse sine of the value gives you the angle. Right? You want the y by itself, divide by 2. And I really don't like leaving it quite like that. I don't like this inverse sine of x over 3 over 2. How about if I write it as 1/2 inverse sine of x over 3? That just feels better. And it equals y, but now that we're done, we switch it back to the function notation with the inverse symbol. Okay? Let's do another. So find the inverse of this function, find the range in the domain. of the inverse function. Okay, so again, they just decided what they wanted our domain to be for this one. They decided they're going to look at the little chunk between negative 2/3 and then negative 2/3 plus pi over 3. Okay, great. Let's see, let's think. Range. If I were going to graph this, I have to put a scale on my y-axis. I look at my function to get my amplitude. The 2 says I'm going to go from negative 2 to 2, so that means my range is negative 2 to 2 inclusive. So I can come down here. I know that the domain of my inverse function is going to be negative 2 to 2. I know that the range is going to be, so the range becomes the domain becomes the range, and I'm just writing it in interval notation because I like that better. So negative 2/3 to negative 2/3 plus pi over 3, inclusive with brackets because they're less than or equal to. All right, so now I want to find the inverse function. I find the inverse function by switching the x's and the y's. So it's easier to get rid of the f of x, so I just write it with a y instead. And let's go back to pink. Okay. So to find the inverse function, I switch the x's and the y's. Everywhere I see a y, I write an x. And everywhere I see an x, I write a y. And then I solve for y. So this one starts the same way, divide by 2. So x over 2 equals the cosine of 3y plus 2. I can't get at the y in this form, so what do I need to do? I need to switch it to the inverse cosine. So just like when I was doing the exponential and logarithmic conversions, this time the inverse cosine of x over 2 is 3y plus 2. I want the y by itself, so let's subtract 2 from both sides. Watch your notation. I'm keeping the x over 2 in parentheses so that it's really clear that that minus 2 is not a part of the argument of the inverse cosine. And then divide both sides by 3. Well, that's just not pretty, is it? Couple of ways you could write this. Yes, you technically could leave it like this. You could also write it as 1/3 inverse cosine of x over 2 minus 2/3. I don't know that that's any better. Do remember to put your notation back. The one in the box might be just as good for this. And again, we have the domain of the range already. Okay, well, a couple more problems. So we're going to find the exact solution. All right, so we want to get at the x, right? We need to move the negative 6. So if we divide both sides by negative 6, the inverse sine of 3x equals negative pi over 6. Can we do it the opposite this time? Can we go the other way? Can we now change it back to the sine of pi over 6 is 3x. Oh, sine of negative pi over 6 is 3x. Okay. We wanted to get the inverse sine of 3x is pi over 6. So we switch it back and say the sine of negative pi over 6 is 3x. Well, we know what this is, right? What's the sine of negative pi over 6? Think unit circle. It's negative 1/2, isn't it? So negative 1/2 is 3x. We want to solve for x. Divide both sides by 3. 1/2 divided by 3 is 1/6. And we are done. Okay, so notice what we did. At the top, we had to divide by the negative 6 because we wanted to get the function by itself. Then because we were after a variable that was in the argument of the trig function and we couldn't get to it, we switched it from the inverse sign back to the sign. Then we use our unit circle to say what the sign of negative pi over 6 is, and then just solve for x. Let's do another. Oh boy, what are we going to do with that? 5 inverse sine of x minus 2 pi equals 2 inverse sine of x minus 3 pi. We want to get like terms together. So how about, can I move this? Sorry that it's not. I have two of those things on the right, so I'm going to move them over so we have them together on the left. I have 3 inverse sines of x minus 2 pi equals negative 3 pi. Again, I'm being careful. The negative 2 pi is not a part of the argument of the inverse sine. Okay, might be better to do that. Okay, so I need to move the negative 2 pi over with the 3 pi. Those are just numbers. So let's add 2 pi to both sides. So 3 inverse sine of x equals negative pi. Needs a function by itself. Let's divide by 3. So the inverse sine of x is negative pi over 3. So I need an angle, again restricted where? Between negative pi over 2 and pi over 2. Okay. And well, I have the angle. I need to find the value. Okay. So let's not confuse ourselves. Let me switch it back like I was going to say the first time. So the inverse sine of x is pi over 3. So that's the same thing as saying that the sine of negative pi over 3 is x. That looks better anyway. Okay, so the sine of negative pi over 3 is what? Think unit circle. Said negative root 3 over 2.